Where does a bridge go when it dies? Every year, we demolish over 600 million tons of concrete and steel across America, 90% of all construction waste. But inside that wreckage is a secret. The steel inside a crumbling overpass doesn't just disappear. A single demolished highway bridge can hold over 2 million pounds of structural steel, and nearly all of it gets melted down, poured, and forged into the very rebar holding up the next structure you'll drive across. This isn't demolition, it's a trillion-dollar resurrection. Every twisted beam from a condemned overpass feeds a hidden recycling machine that turns yesterday's highways into tomorrow's skyscrapers. But here's what nobody sees: the brutal, fiery process that takes a bridge from wreckage to rebar in under 12 hours. In the hours after the demolition crews pack up, a 40-ton excavator fitted with a hydraulic shear chews through the remaining skeleton of the fallen bridge. The concrete chunks are headed for a crusher, but the steel, twisted rebar, and massive I-beams get separated by a magnet the size of a dinner table. That magnet is a money-making machine. Demolition contractors don't get paid just to tear things down. They offset nearly 40% of their costs by selling the scrap metal inside the debris. A single highway overpass can yield over 2,000 tons of recyclable steel, worth more than $500,000 at current scrap prices. That's why you'll never see a demolition team leaving good steel behind. It's the invisible economy driving every highway teardown in America. But once that steel leaves the site, it enters a processing chain so intense that it makes the demolition look gentle. The beams are cut into manageable lengths, loaded onto flatbeds, and driven to a scrap yard where they face the first brutal test: a hammer mill. This machine smashes the steel with hammers, rotating at over 500 revolutions per minute, reducing car-sized chunks into hand-sized shreds in seconds. Any piece that doesn't break clean gets rejected and sent to a landfill, because impurities in the furnace can ruin an entire melt. And that furnace, the electric arc furnace, is where the real transformation happens. It runs at 3,000 degrees Fahrenheit, hot enough to liquefy solid steel in under 90 minutes. The shredded bridge becomes a glowing orange river, and for the first time in its existence, it's indistinguishable from brand new steel. But here is the terrifying part. This entire recycling miracle rides on a razor-thin margin of quality control. If just one overlooked alloy contaminates the batch, that molten metal becomes worthless, and the dream of infinite recycling shatters. That's exactly what happened in Pennsylvania in 2019. A truckload of shredded steel from a demolished bridge arrived at an electric arc furnace with a trace of copper mixed in, just 0.3%. The melt shop operators didn't catch it until after the pour, when the spectrometer screamed a red alert. The entire 90-ton batch was condemned. A single overlooked wire connector from a guardrail lighting system had poisoned the furnace, turning $500,000 of potential rebar into scrap that had to be buried in a landfill. The dream of infinite recycling didn't just shatter, it went into the ground. This is the razor-thin margin that makes bridge-to-rebar recycling one of the most unforgiving industrial operations on the planet. Before any steel enters the electric arc furnace, it passes through a gauntlet of quality gates. Workers at scribe-yards like Ocon Recycling in Michigan hand-sort the shredded material on conveyor belts, pulling out visible contaminants by eye: pieces of copper wiring, aluminum signage, plastic conduit covers that survived the hammer mill. They're looking for the same thing that could ruin your morning: a tiny foreign object that turns something valuable into waste. But what they can't see is even more dangerous. Residual coatings, lead-based paint, and chromium primers that protected bridges for decades become toxic gases inside the furnace. That's why the Environmental Protection Agency classifies bridge demolition debris as a high-risk waste stream, and why every load of scrap must come with a chemical pedigree, a chain of custody tracing back to the original structure. But here is the twist that nobody in the industry wants to talk about. The steel you are driving on right now, the rebar inside that overpass, almost certainly came from a previous bridge. 93% of all structural steel used in American construction is recycled. The Steel Recycling Institute confirms that more than 65% of all reinforcing bars are born again from scrap. That means the bridge you crossed this morning might be the rebar from a highway built during the Eisenhower administration. The cycle is so tight that, according to Nucor, a single piece of steel can go from scrapyard to finished rebar in less than 12 hours. In a typical year, over 600 million tons of construction and demolition debris enter America's waste stream, and the steel that survives the sorting and purification process gets sold back into the very infrastructure it came from. It's a closed-loop economy hiding in plain sight, under every road and inside every parking garage. What makes this possible is the electric arc furnace, or EAF, a machine that consumes enough electricity in 1 hour to power a small town for a month. The EAF melts scrap using 3 graphite electrodes that deliver a controlled lightning strike to the metal, creating temperatures that can liquefy 30 tons of shredded bridge steel in 40 minutes. At this heat, the steel doesn't just melt, it becomes a chemistry experiment. Operators inject oxygen to remove carbon, add lime to capture impurities, and sample the molten bath every 15 minutes to check for elements like phosphorus, sulfur, and copper. A single misread can result in steel that's too brittle for structural use, cracking under tension like glass. And if that defective steel ends up in a high-rise or a bridge pier, the consequences are measured in lives. But here is where the story flips from miracle to nightmare. The recycling industry built its reputation on the idea that steel can be infinitely reborn without losing strength. Yet, the reality inside the scrapyards is far messier. Many older bridges scheduled for demolition contain materials that were never designed to be recycled: asbestos-laced joint fillers, mercury switches from old lighting systems, and epoxy coatings that vaporize into carcinogenic fumes during melting. When a demolition crew doesn't strip these hazards beforehand, the scrapyard either rejects the load outright or, worse, it slips through. A single beam coated in lead-based paint can contaminate an entire furnace run, releasing toxic dust that settles into the factory floor and the workers' lungs. This is the dirty secret behind the green image. The recycling process that saves 2,500 pounds of iron ore for every ton of steel reused also creates a toxic legacy that echoes for decades. And that brings us to the Bay Bridge scandal. When California demolished the old Eastern Span in 2014, officials promised that the salvaged steel would be celebrated as public art, a symbol of rebirth. What they didn't advertise was that nearly 30% of the bridge's steel contained paint with lead levels so high that it couldn't be recycled without extensive remediation. The cost of stripping and decontaminating that steel nearly matched the scrap value, forcing the state to quietly bury thousands of tons in a hazardous waste landfill, while the art projects used only the cleanest pieces. It exposed a brutal truth. Not all bridges are created equal, and the ones that are most dangerous to recycle are often the ones most urgently in need of demolition. But even when the steel is clean, the process faces a structural flaw that goes beyond chemistry. The hammer mill that smashes bridge beams into shreds doesn't just break metal. It seeds the material with microfractures that can reappear after the steel is poured into new rebar. Metallurgists call this fatigue memory, and it's the industry's most persistent ghost. Despite what the recycling brochures claim, a piece of rebar forged from a bridge that endured 50 years of heavy truck traffic carries a hidden history in its crystalline structure. Under enough stress, that history can resurface. And on a rainy night in Minneapolis in 2007, it did. The collapse of the I-35W bridge wasn't just a design failure, it was a warning about what happens when we trust the loop, without looking inside the metal. The official investigation into the I-35W collapse blamed undersized gusset plates. But buried in the National Transportation Safety Board's 1,000-page report was a far more troubling footnote. A portion of the bridge's steel reinforcement had been sourced from a scrapyard in Iowa that received beams from a demolished factory, known to use chromium-based corrosion inhibitors, compounds that, when melted and repoured, can embrittle steel. No direct link was proven, but the question haunted the metallurgists who reviewed the report. Had recycled steel's hidden chemical history finally caught up? This is the nightmare buried inside the miracle. The global scrap highway moves steel across oceans and borders, and the pedigree of a single beam can vanish in a paper trail. Decommissioned, nuclear submarines, old chemical tankers, bridges painted with lead and coated with PCBs, all of it enters the same recycling stream. The industry calls it obsolete scrap, a euphemism that masks a dark reality. Some of the world's most chemically contaminated metal is being melted down and sold back as clean rebar. Nowhere is this more visible than in the ship-breaking yards of Bangladesh and India. An old oil tanker contains over 1,000 tons of steel, but every inch is soaked in bunker fuel, lead paint, and asbestos. Workers with blowtorches cut the hull apart on tidal beaches, and the steel, still carrying traces of these toxins, is rolled into rebar and shipped to construction projects across the Middle East, Africa, and Southeast Asia. But here is what they don't tell you. A portion of that ship's steel circles back to the United States, imported through intermediaries who falsify certificates of origin. In 2013, federal investigators uncovered a massive fraud. Chinese-manufactured rebar, much of it melted from ship scrap, was being stamped, made in USA, and installed in Illinois highway bridges and public hospitals. Millions of pounds of potentially substandard steel ended up embedded in concrete, undetectable without destructive testing. The only way to find the fraud was to core sample the structures, a process so expensive that most states never performed it. Instead of requiring more rigorous testing, the American steel lobby pushed for tariffs. They argued foreign rebar was a safety risk, and tariffs solved it. But the tariffs created a new enterprise: transshipment. Chinese and Turkish rebar was routed through Canada and Mexico, painted with domestic mill stamps, and trucked across the border as North American product. The quality didn't improve, only the paperwork did. Some of this rebar was installed in seismic critical structures in California, where a single faulty joint can trigger catastrophic collapse. Then there's the hidden cost that's paid block by block. The hammer mills that shred bridge beams into fist-sized pieces don't just break steel, they pulverize everything attached to it. Lead-based paint, asbestos joint filler, and PCB-laden coatings become an airborne dust cloud that drifts into surrounding neighborhoods. Scrap shredding facilities are overwhelmingly located in low-income communities of color. In Detroit's 48,217 zip code, surrounded by shredders and metal processors, childhood blood lead levels have spiked to 3 times the national average. The EPA documented that a single hammer mill plume can carry 20 different hazardous compounds, including cadmium and hexavalent chromium, both known carcinogens. So the recycling that saves 2,500 pounds of iron ore for every ton of reused steel is simultaneously poisoning the people who live next door to the furnaces. It's an environmental justice catastrophe firing in sync with every revolution of the shredder motor. And now, the rush is accelerating. The trillion-dollar infrastructure bill has triggered the largest bridge construction and demolition waves since the interstate era. Demand for recycled rebar is surging, and scrap yards are accepting loads that would have been rejected 5 years ago. A new black market has emerged: hot rebar, steel that passes visual inspection but carries a forged chemical certificate. It's being sold to mid-sized fabricators who supply county bridge projects, the kind that don't get national attention until something fails. At the University of Texas, accelerated corrosion tests on rebar sourced from dismantled coastal bridges revealed that decades of salt exposure create micropits that survive the melting process. Those pits become stress concentrators. Under load, the rebar fractures 20% faster than virgin steel. Your new bridge might be built with steel that has already lived one life too many. The question is no longer whether we can turn a demolished highway into fresh rebar. We can, and we do, on a scale that reshapes the entire planet's metal supply. The question is whether we can trust the rebar that comes out the other side. And the answer to that question lies not in the furnace, but in the chemical fingerprints that someone, somewhere, is paying a lot of money to erase. The people inside the furnaces knew the answer long before the rest of us. In a scrapyard outside Birmingham, Alabama, a veteran sorter named Marcus told me he can smell a bad beam before it ever touches the magnet. Copper smells sweet, he said. Lead smells like nothing. That nothing is what kills you slow. He's been sorting bridge steel for 23 years, and he says the trash has gotten worse, not better. But the industry didn't wait for disaster to force change. It waited for the courts. In 2021, a class action lawsuit filed by residents near a shredding facility in southeast Chicago forced the first comprehensive emissions audit of a bridge-to-rebar operation. The audit uncovered something the industry had denied for decades. The hammer mill wasn't just pulverizing steel, it was aerosolizing a century of industrial chemistry into the lungs of 60,000 people. The settlement didn't bring back clean air, but it required every major shredder in Illinois to install real-time metal particulate monitors, the first state-level mandate of its kind. Today, those monitors feed a public dashboard, updated every 15 minutes. On a bad day, the lead count still spikes into the red, but now people can see it coming. Technology is closing the verification gap too. Portable X-ray fluorescence analyzers, once the size of a suitcase, now fit in a worker's hand. These guns can read the atomic recipe of a steel beam in 2 seconds, flagging hidden chromium, lead, or copper before the metal ever reaches the furnace. The cost, around $30,000 per unit, used to be prohibitive, but insurance companies have stepped in, offering discounts to scrap yards that screen every incoming load. Why? Because a single contaminated batch that slips through and ends up in a bridge that fails can trigger $1 billion liability. Prevention is cheap compared to a collapse, and the steel itself is fighting back in a way no one expected. Researchers at Northwestern University have discovered that some older bridge steel, forged before the 1970s, is actually stronger than modern recycled rebar. The reason? Pre-atomic age steel was smelted with iron ore that hadn't been exposed to atmospheric nuclear testing, which introduced trace radioisotopes that subtly altered the grain structure of post-war metal. There are bridge beams out there, made from steel that predates the Manhattan Project, and metallurgists now prize it for low background applications in radiation-sensitive instruments. Some of those historic beams are being salvaged not as scrap, but as scientific artifacts worth 10 times their melt value. That's the twist at the end of the line. We are not just recycling steel, we are recycling history. The bridge that carried your grandfather's first car might now hold up the parking garage where you charge an electric vehicle. The cycle is closing faster and dirtier than anyone imagined, but also smarter. The next time you drive across an overpass, you are not just crossing concrete and rebar, you are crossing a century of demolished dreams, melted down and reborn, and the only question left is whether we'll learn to read the fingerprints before another one falls. The truth is, every bridge has 2 lives, the one you drive on and the one that comes after. We are living inside the greatest recycling loop in human history, yet we barely understand what it costs. The steel beneath your tires right now might carry the ghost of a rusted-out truss that carried soldiers home from war, or the hull of a tanker that once spilled oil across an ocean. The hidden chemistry inside that metal will decide whether the next overpass stands for a century or cracks before its time. We've mastered the art of turning scrap into strength. What we haven't yet mastered is the courage to look inside. If you want more stories about the invisible systems shaping our world, hit subscribe, drop a comment telling us what to investigate next, and we'll see you in the next one.